So Chris, it's great to meet you. Great to be here in Schaffhausen as well.
Welcome to Schaffhausen, yeah. So, welcome to the northeastern corner of Switzerland, and this is quite far away from the Swiss watchmaking valley.
Yes, most of the manufacturing sites we go to, it's always in the Swiss France part of the country, so this is a little bit of a different idea, but it's very specific to IWC's history, correct?
Yeah, I think it's linked to the industrial base of this region.
Yes.
So Stuttgart, the German car industry, is an hour up the road. Here you have a great engineering base. Schaffhausen for centuries was making industrial products, was making trains later on, even guns for the military, all that sort of industry is here. So when Jones crossed the Atlantic from Boston to set up IWC, he really realized that this environment here was very pro-entrepreneurs. It was very tax-breaky. It was very good to set up a business. And I think that's what brought him all the way here, because Mr. Moser, who he met somewhere in western Switzerland, he owned a hydropower station here on the Rhine. That gave him the power. He could build his building here, and that's how we ended up as the international watch company in this corner.
Talk about this structure as well, because you were part of really designing this new site.
Yeah, my background is really in interior design, in shop design, exhibition design for IWC. So this was a really, really cool project because something like a factory obviously lasts a lot longer than a shop or an exhibition. And to create kind of the watchmaking home for IWC was a really, really fun exercise. And what we wanted to do here is, you can imagine our previous facility, our main headquarters, is really stuck between the River Rhine and a very historic old town. Everything's listed buildings, heritage protected. So you end up with this sort of chaos of buildings, and it's many floors and levels. It's not very logical for watchmaking. So here we had tons of space. So we said, let's really tell the story chronologically from a raw bar and plate of metal all the way to a finished watch movement and finished watch case. And that is really, this facility is laid out so you can really understand how that raw material turns into a finished watch.
And then talk a little bit more specifically about what we will see today on this tour.
So in this facility here, you see all of our component making. We make over 1,500 different watch components here, going into Ebosch, going into all of the assembled products. And then we see watch assembly. So you see both fine watchmaking and inline watchmaking for our main commercial references, chronographs, automatics, and so on. Then we go into case making. So you'll see cases being made from ceramic, from Ceratanium, all the metals, all the precious metals, decorating, finishing, all the handcraftsmanship that goes into it. And finally, dial pad printing, and then we'll finish the tour. Right, so here's really where it all starts. So this is the start of component manufacturing, where you see some of our smallest components being milled and machined and turned, and it really starts with sort of, tiny diameter, couple of millimeter rods. It might be brass, might be steel, might be aluminum. And then from there on, you can really see some of the smallest parts, where this is one of those regulating clips that sits on the hairspring. And this is the technical drawing. Then you look at the actual piece, it's just in here. But basically, you can barely see it, right? Look at some of these components. They really are micrometer. So all in all, it's over 1,500 different components we're making here now.
So you're working on probably larger components like bridges, wheels, but then you can get down to a very fine detail as well.
Yeah, absolutely. Some of the mechanisms like perpetual calendar, they really require some absolutely dainty levers and gears, and that is what these ladies and gentlemen here are really focusing on.
And then in terms of like the process too, I mean, like I'm sure there's like prototyping that happens very much in this facility as well, in this department specifically.
So this does prototyping, it does small series, and then whenever we do larger series of gears, screws, etc., we tend to not make them in-house. We have our own gear manufacturer that is external but belongs to be partly invested in. And those would be the kind of suppliers that make the large series of components. Smaller series, individual ones, they're all made here.
So Chris, can you tell us a little bit more about the machines as well and like what you have here?
Yeah, so this is all the milling machines, CNC centers that make components and make some specific things like our new hard ceramic machining. This is something really introduced very recently. So this is all a diamond tool CNC machining of finished sintered ceramic blocks. So especially in prototyping for ceramic watches, that is the way how you can get to a ceramic prototype quite quickly. Now these CNC machines, they're all multi-axis, front, back, all at the same time. You see here, for example, that is a sintered finished block of white ceramic, already heat treated. And then you can use diamond tooling to actually mill out case elements like that, finish them, machine them, polish them, getting everything to like a first impression of what a future ceramic watch.
And even to get to this point, when you have that sintering process, you have to think about like the scale, because I know that ceramic can shrink very dramatically beyond what you need it to be for a case.
In the beginning, there's two interesting points here. Firstly, like none of the ceramic colors apart from white are the same color in powder form as they are in sintered block. So for example, Mojave and the Woodland, they tend to be quite pink. The black ceramic is quite brown as a powder, and then you make it 1/3 bigger than the final product. The soft powder is compressed and machined, and then when it's sintered, it shrinks down by this about 1/3 to its final shape. So mathematically, it's quite complicated.
And then the cutting, you have to use a diamond tool because it's really the only thing hard enough to actually
1200,
shape the case.
1300 Vickers, only diamonds will do the job.
And as we continue forward, what else can we see in this room?
So all of this is our CNC machining. So you have traditional CNC machining where you have a single-sided operation in your metal workplate. And then we come to really the latest generation of these very specific component making CNC centers. So what you see here is 7 of these double-sided CNC centers. And what happens here is basically you have a fully automated loading process for the brass plates into the CNC machine. You have all of the tool magazines with over 100 different tools that the machine can pick. And then it actually flips the movement base plate. So as you machine one side of the base plate, you don't want to have any quality issues when you do the other side. So these machines basically are able to flip the plate and have absolutely zero variation when they machine the backside. And this is still one of the most complex parts we put into a watch.
Absolutely.
Because here you have all of the different machined areas, you have different
all those pivot points that you have to
pivot points have to be spot on, where the stones go later on. And by achieving this both from both sides at the same time in the same process, you really have 100% quality control over the outcome.
So here we can see the different tools for the CNC.
Exactly. Yeah, so this is really, it's an automatic loading magazine. You have over 100 different tools and drill heads and CNC machine heads that are being used in the process, and the machine is really able, depending on what we're working on, to pick the right tool for the right job at the right time, making that whole process a lot more fluid. You can also see here, this is basically the automatic loading of the brass plates into the machine, and then the removal of all of the finished work plates that get put into storage here, so they can really run 24/7. So this is basically the next process step. When those finished machines components, they go into here, and then they're just being cut out of their holding plates. Right? So there's still the residual brass plate holding the piece in place, and this is now the CNC cutting process where the excess metal is being removed before it goes into deburring here just on the other side. And there literally we use tumblers with different aggregates, from ball bearings to stones to nutshells, that remove all of the excess metal. And in the end it goes into our watch spa here, which is a very elaborate washing machine. And then all the oil gets removed, and then you have a finished raw part that's ready for stone setting, which is the next step.
Can you explain why it's so beneficial to remove all that excess metal in the movement, especially even for these smaller parts, because a lot of people think finishing only happens later in the stages, but even from a machine level at those base components that needs to be considered as well.
Yeah, it's absolutely key, because obviously the last thing you want is any micro filament of metal that could come loose in the movement and ultimately clog up with the oil. It would impact chronometry and precision. So from the start of even to the bare eye, of course, these parts look almost, completely perfect. But on a microscopic level, there's always something happening to the surface, some excess metal here and there, and all of that needs to be removed in order to have a precise part for the next process step. And that's right here. So stone setting, as you may know, you have these lab-created rubies, right, which are basically the bearing points for all of the moving parts inside a watch movement. They come from very small size to quite larger size, and they have a top and a bottom because they have a little dip and a dimple on top where the oil will ultimately sit before the gear will actually interact with the base plate, right? And all of these different stones, they have to be set correctly, correct size, correct positions, and at the correct depth. And again, we've invented quite an ingenious little setup and machine to help us with that.
And we could be talking about dozens of different joules in one movement depending on the complexity, and you do a lot of high complications here at IWC, so this can all be structured around what the needs are for that specific movement.
So it all starts off with a fun sorting process. I'll just open this up for you, we can have a look. So basically, we have a little chute, all the rubies go in, they get shaken on that rubber plate. A camera will take a picture, you see the green light flash in a minute, and then the little vacuum arm will pick up every single ruby that's the right way around. When it's done, it shakes them again, it takes a photograph, you can see it there.
So it'll know exactly the precise precision.
It knows which one is the right way up and which one is not, and then adds it to these magazines, which we make in-house, which are ultimately where the rubies are being picked from to go into the watch movement.
So some of these kits and these trays for the actual rubies, you're actually going to, in the same department, you'll actually machine those
here? You'll see this downstairs in the machine shop. All of these machining aids, they're all done by our apprentices here in the machine shop. It's part of their CNC apprenticeship. So once the magazines are filled with rubies, you have this machine that we developed together with our machine partner, where you will actually see that every time it identifies in the movement base plate which ruby it needs, which position, at what pressure, it will pick the right ruby, it'll insert it, and then check immediately that all of the quality is 100% correct. And that way you end up with all of the rubies set 100% quality control before we go into the decoration.
Now we're here at Casemaking, and one thing I want to talk about here especially is this is one of the common aspects of watch production that is outsourced. But here at IWC, this is one of your specialties because of this material ability that you have. Yeah. So talk us a little bit through about what we're looking at.
Yeah, this is really our raw metal rod store, where it really, from brass to aluminum to stainless steel, bronze, titanium, ceratanium, platinum, gold, white gold, red gold, all of those start here. So you can really imagine like all of these special alloys, they come in rod form, they get sliced, and from the slicing we really turn and mill this into a raw case shape or raw bezel shape or raw case back shape. And it's sometimes amazing just to remember when you compare the weight of stainless steel, which is this one.
Oh, should give me a warning for that.
Steel is quite heavy, and then you compare it to titanium or ceratanium. There's really a marked weight difference, which really comes across when you hold the raw bar of it. It's good for the gym.
Yeah, it is. Yeah. Get some bicep curls in, huh?
And then ceratanium, of course, which is completely unique to us. You see, it looks roughly like titanium before it's fired, but because of the ceramized particles in the alloy, once it gets heated and fired, we get this like really deep, dark gunmetal kind of finish to the material.
What's the challenge with this alloy? I mean, you're combining both, the titanium part of the chemical makeup with ceramic. I would imagine from like even just getting this rod into its form is probably difficult even.
Yeah, it's an excellent question. We'll see it in a minute. But the main challenge is to have a perfectly even distribution of all of the different components of the alloy across the rod. And what we worked out, even in smelting and forging, if it's under control, when you come to extruding the metal into different diameters, it reshuffles the the structure of the metal in the alloy. And this is where we had a lot of problems in the beginning with inclusions, with rainbow effects once it's fired, where you've got these weird colors happening. And we found out that we really have to heat up all of the material during extrusion. You can't cold extrude it, and that is then the path to actually getting to even distribution. But it's always in R&D, before you understand these effects, everyone is a bit baffled because you don't quite know where it goes wrong. Because you have the alloy, which is perfect, you have the forged bar, which is perfect, and then you come to fire the component and it's just not working. So this is always the iterative learning of how to actually process material in the end.
So you start with these rods. Now, how are the cases actually formed?
It happens in these big 5-axis machining centers left and right here. You basically feed the rod into this huge salami slicer, as it were. You again have all of the tools. Everything is a bit more heavy duty compared to what we've seen upstairs in component making. We're working with bigger parts here, working with harder materials. And then you have all of the main case shaping, drilling and milling operations done here in one go before they then get moved on for surface finishing, engraving and decoration. And again, I want to show you as well, in terms of being as cyclical as possible, all of the excess metal gets pressed into pellets, it's fully recycled. All of the oils from the machine is a closed circuit of recycling, of cleaning the oil. Water comes off the roof, a lot of rainwater, you've seen that today, being used in manufacturing as well. So we try to keep everything as closed cycle as possible in our manufacturing.
And then you melt this down and then reform it into the rods that we just saw at the beginning here.
Exactly. So Ceratanium really is a combination of the best elements of titanium with the best characteristics of ceramics, which is all about the hardness on the surface and scratch resistance. And we've used Ceratanium in quite a wide range of watches. So from a simple chronograph and double chronograph in the Top Gun series to our unique time zoner, where you have this bezel system where you just press down and you change the time zone at 12 o'clock, and it's fully synchronized even across the date line, so you can play with it forward, backwards. Movement never loses a beat. Perpetual calendar and the big pilot on a full Ceratanium bracelet, and then my personal favorite, which is the shock absorber XPL, with a mechanical wristwatch that protects the movement against acceleration forces of above 30,000 G, where we stopped testing. And you can imagine, if you have your wristwatch on and you really whack the table, you're probably going to generate something like 1500 G inside the watch case. This takes 30,000 G, and still the watch movement survived. And I find that fascinating because when you see a watch movement being assembled, you see the intricate parts. I'm surprised it survives any shocks, but getting this up to 30,000 G by suspending it in that BMG spring and decoupling the winding mechanism from the movement. That's really been quite a breakthrough for us.
Where do some of these acts of innovation come from? Do they come from requests for, because you have all this the aviation connection and all these extreme environments that your watches are needing to withstand? Like where does this come from? Like Ceratanium is not like something you just wake up one day and say, we're going to make this. Like where did this all come from? Why do you have this desire?
Ceratanium was really an internal development. Titanium was a question of the hardness at the end of the day, the lightness is there. And ceramics is always the question, you always have to make certain adaptations to your case design for ceramic because of that risk that a too thin ceramic part could fracture under pressure. Right? So we wanted to solve that issue by combining really that toughness of titanium with the surface characteristics of ceramic, and that's why Ceratanium was really a development that came from us. The shock absorber was direct feedback from our US Navy pilots, because we've seen, especially in the FA-18 Super Hornet, it's still a analog digital mixed cockpit, and everything is metal, and the watches get banged about a good amount. Like when you look at the prop watches that went to Top Gun Maverick, you know, we had some PVD coated watches there because they all had to be done really quickly, and they came back absolutely battered. And from that insider seeing just how these kind of instruments have to, you know, survive, you know, these extreme circumstances, that's really when we started to think about, okay, what could we do to really shock protect mechanical movement much more than it is in standard watch. Ceratanium, totally unique process. You have this electromagnetic smelting process, so you end up with residual metal. It looks like that. It's quite funky. You also see that rainbow effect I was talking about inside, you know, that can happen in the metal. It then gets forged in the Highlands in Switzerland in Bern, and then we start extruding from the forging process into the different diameters you need for watch manufacturing, for smaller parts like crowns and pushers, for case rings and actual cases. Then we machine like titanium. We sandblast those components, and then they get fired to that finished product, which then gives you that deep gunmetal effect versus the raw part you see here in that double chronograph case. Now we've machined our raw cases and our raw case backs. Now it's all about the finishing and decorating and turning it into that look and feel that you ultimately carry on your wrist. And one of the key innovations here in this whole axis of engraving is all about laser engraving. So laser engraving, if you know how to program a laser, is an amazing technology to get to really beautiful three-dimensional light facets and engraved effects. It's a multi-level programming that makes sure that the laser goes to certain depths, to certain angles, and it allows you to produce really intricate patterns. When you think about our Chinese New Year editions, right, you have dragons on there with scales. That's only possible with laser engraving, and that's something that's still relatively new. So here, for example, you see the Top Gun caseback engraving for the Top Gun logo that's on our Top Gun watches. That's all being done here with laser engraving before we then go to the next step, which is all about the case finishing, the polishing, the brushing, and making sure that all of the final anglage and all of the accents are here.
Wow.
And once again, this is a 100% manual process. So you literally have muscle memory in the very, very skilled operators that have been doing that in many cases for many years. And this is a constant polishing, brushing, visual checking, using the loop to make sure everything is up to standard, and then finishing every case individually.
And then they might be using like diamond tools or for polishing here because it's for like a higher...
Diamond we'll see in a minute. Okay. So, you know, as we're working on stainless steel and similar materials, those are not diamond tools, but then for the actual edge and bevel finishing, you'll see diamond tooling.
So you'll use larger wheels for like the bigger surface areas that need to be polished, but then for those fine points, you might have to use, you know, diamond tools over here for that kind. Yeah.
You also see that the gentleman here is using a special holding device that actually holds all the surfaces of the case in lugs as he needs to machine them, so it gives him perfect access to the surfaces he's getting to. And this, you know, now we have a case back ring, but this also works when you have lugs to be polished so that you protect the side elevations of that lug and just go to the top section which you want to polish.
So do the polishing. He's always going to inspect after every surface.
And it's all about feeling, you know, this really muscle memory from feeling the pressure in your hands and arms. And it's something that's just, I always, you know, it's so human.
What is it about the human touch that is so crucial for this step? Because I mean, you would think that, we have this very complicated material type. You know, why are humans intervening here? Why is that important for you at IWC to have this step?
Well, I think it's really interesting about this idea of these analog machines having a soul and a character, and none of these watches, none of the movements, none of the cases, none of the dials are really identical in the end. And I think in terms of forming a relationship, a watch is something we hold on to for a long time. And I think we like things that have edges and have a bit of character. And many electronic devices, they're 100% the same. When you think about software, it's 100% the same when it's replicated. At the end of the day, every watch has had this human touch, and every watch has its own different character, its own different heartbeat. So for example, we're now introducing an authentication system called Hawkeye, which actually takes a high definition picture of a watch movement and a watch dial. And that is enough. By looking at 250 points plus on a watch dial and a watch movement, you can tell them apart, every single one. Right, so you'll be able to visually identify each watch individually.
So now here we're looking at like inside the lug, or like that faceting and the beveled edge right here. Yeah. So you need a smaller wheel to be able to make these cuts.
Yes. Yeah.
Like, what are the different types of machines? So you have these like fine-tuned wheels that are going to be able to get these small detailed, beveled edges. I saw like a spinning, is like a Zales machine, something of that sort.
The brushing wheels, which give you that very, very nice horizontal brush on the case. You have the softer machines for the polishing elements on different materials, and then it goes all the way to diamond cutting, really hard materials on those beveled edges to get that perfect final definition of what you'll be seeing in terms of light reflections on your wrist.
And then what's the inspection like for like the quality check for like polishing at each one of these stages? Because I would imagine it's going through some different hands.
It happens right over there.
Oh, look at this. I'm reading your mind again. This is great.
Look, surface control. This is really, the ladies with the very Hawkeyes are working here. And really you can see it right now. They're hand inspecting every single case part in terms of the aspect check to make sure that everything passes or not. And if need be, we rework. But again, making sure that when things go into case assembly, everything is 100% quality checked. Ultimately, we don't want a quality department. We want every manufacturing step to be completed at 100% before it gets passed on. Because the last thing you want is notice something right at the end, have to disassemble the watch, disassemble the movement and fix something. It's much better if every step is quality checked 100% and you end up with a much more efficient way of assembling watch.
When you're finishing a case, I mean, you're basically removing material from a case. What if they inspect something and there's almost too much material taken off? Like, what happens to that case? Do you have to melt it down completely? Do you have to start from like over, basically?
That's not going to happen here because I think in the beginning we're talking about such small amounts of metal that you're not going typically to get to a point where too much metal has been taken off. Yes, of course, in customer service and repairs, many years down the line, you will have these situations where there's too much metal gone. And then there's, which is amazing to see, our silversmiths and goldsmiths actually working by hand to laser weld material back into the case part and then to repolish and refinish it. And I've just had the demonstration again from one of our goldsmiths a couple of weeks ago. And when he patches up a really deep hole, and he actually sort of whacked it with a hammer and got a big chunk out, and laser welded it back in place and finished it, I can't tell where that spot was. Like, not at all. Even if you look at it in magnifying glass, you cannot tell. So it's amazing how they're able to restore. And then, of course, at some point, if it's all polished away, you might have to replace a case component. But we're talking here 50, 100 years down the line.
So, Chris, now we have dial printing, and also beyond that, printing of other smaller parts as well for indicating whether it's power reserve indications, outside bezels, correct?
Yeah, absolutely. So this really started off with the Aqua Timer challenge for us, because if you have an internal rotating bezel that's at an angle, and it's very, very complex to bring the superluminova and the pad printing actually onto that shape. And after being continuously dissatisfied with the quality we're receiving, we started to develop this ourselves, and we've become sort of a bit of an expert in pad printing. It's something we really specialize on, and we're doing some really intricate parts here. You see, for example, these star charts that go into that Portuguese Sideral, which is a customized star chart. You see things like the Eternal Calendar dial, which is a glass dial, right, with that opening for the 400-year gear. You've got these complex rails. This is an Eternal Calendar one, but then also some really sort of fun and interesting special things. From the military series, we have 25 years Top Gun instructors in Fallon, Top Gun watch, different bits, Vegas special edition, where you have that roulette wheel. Where I had to learn that roulette doesn't actually have alternating red and black numbers. That was quite a brain teaser for me to learn at that point. And then also something like this is the crew watches of the Polaris Dawn mission Jared Isaac manned SpaceX last year, individually marked with these Polaris Dawn crew patch, Star Sky in the back. So these are typically the watches for movies, for example, we do here as well. So all these special jobs.
Can you explain a little bit more about like the process, like for the machine? Like, you know, have these pads that will take up ink, or
so basically the pad will be cleaned with something like alcohol every time in between every single print, and then it's all about picking up the paint or the ink in that case, and then it's a question of how long and how many times do you press down on where you want to print, and how you get from the master, which in this case, for example, isn't round but actually oval shaped, and then as it compresses and picks it up and transfers it onto the shape, you end up with a perfectly round print. And this again is sort of iterative learning of exactly how hard, how long for, and how many times you print before you have a really, really good result in terms of your paint coverage.
And then when you're doing this print, is it more just for indication, or is there also like superluminova that's applied afterwards, or is it applied, okay, it's afterwards?
It's typically applied afterwards, yes. And then you also have an interesting case in hand, and I think that actual part is gone now, but you had the Palweber where the digital indication on the discs happens for the jumping hours and minutes. And in the beginning of the development, that mechanism kept getting stuck, and we didn't understand why until somebody figured out that the different center of gravities for the weight of the numbers printed makes those discs unbalanced. Right? And in the end, we had to actually use lighter paint and a lighter print to actually make sure that because of the different weight of the 8 versus number 1, you don't end up with a sort of unbalanced effect when those discs are turning and switching quickly. So sometimes it's just part of the R&D as well to try out different paints, different print weights, and make sure that in the end you have a very balanced component if it's a moving one.
And you'll also print on things like sapphire as well?
Yeah, sapphire or glass indeed, we do. You know, this is typical glass backprint, a Lewis Hamilton edition here, or an AMG edition, or the things we do for Loris. And then really one that we're very proud of is our moon disc printing. So it's a very small part, and you can see that you have these polished moons and the little stars, and then the night sky is perfectly printed in between the stars. So right here you can see pad printing in action. So the first step is see that the operator will place the print medium correctly into that hole that needs to be 100% calibrated. Now the machine will calibrate itself and make sure that the pad alignment is 100%, and now actually it moves over, it picks up paint, it goes back to the print medium and actually now does a first pass. I make one pass, I'll make a second pass, and then the part is printed and we go back to cleaning the pad before the next part is inserted. That's really pad printing.
So Chris, now we're behind the scenes of watch assembly here at IWC. So it looks like there's a variety of ways that you have this set up. There's a couple different rooms. Looks like high complications happen here, and then more of your standard production types of pieces and movements will happen back there. Is that correct?
Yeah, absolutely. This is the heart of the facility. It's an over 1,000 square meter clean room. Absolute perfect conditions for watch assembly. And as you mentioned, you know, we're working both in sort of a shared team line assembly, where the idea of you know, a standard chronograph and automatic movement is really to make sure that the quality and finishing level is as constant as possible, because when these watches go into service later on in Dallas, in London, in Dubai, you really want to be able to, for every watchmaker, for every spare part, for everything to be as constant as possible. And so the idea there is that watchmakers are sharing the work, they assemble different stations. When people are off sick or they're on holiday, you can actually subsidize that, substitute it with somebody else, and it's a very sort of team approach to assembly for even quality. And then you have fine watchmaking, which is Perpetual Calendars Plus, where it really is all about one watchmaker, one watch. And you see that also in terms of assembly, whereas usually for our main watch lines, we typically assemble the movements here and assemble the cases downstairs, but then take them to our headquarters and finish the assembly there with a dial, the hands and the glass. You'll see that here in fine watchmaking, the entire watch head is assembled, disassembled, tested. So you end up with a complete watch head that comes off the desk and the bench of one single watchmaker.
So when you start getting into perpetual calendars, high complications, this is where you'll have one watch for one watchmaker.
Exactly, yeah. And you also have both the assembly of the base movement and the assembly and the marriage, as it were, of the module, both happening in the same step, which makes sure that there is really one regulating watchmaker that does everything from start to finish.
Could we talk a little bit about like watch education for IWC, because I know. Oh, well, fantastic! I read your mind. So in Schaffhausen and your other facility, you have a school associated with that, right? Correct? Is that true?
Well, yes. So it's our apprenticeship program, and this is on the one hand is watchmaking in a 3 or 4 year program, but it's also CNC machining, surface polishing.
Oh, so all aspects of watch manufacturing.
Yes, and it even goes all the way to designers, mediamatic people, business apprenticeships. So in Switzerland, and especially here for us, where we don't have the Valet de Joux kind of a jobs market out there, we really train all of our watchmakers here. So we have an intake of between 8 and 12 watchmakers a year. They will graduate after 3 to 4 years.
So what's the typical like path for somebody that's in this room behind us to get into fine watchmaking? Like how long does that typically take?
Well, it can take literally 10 years plus, maybe start in line assembly, start in simple watchmaking tasks. Then people have different drives to develop at different speeds. Watchmaking is quite an introvert profession. It's not something where,
there's some isolation in watchmaking for sure.
There's some concentration necessary. And it suits certain types more than others, and especially fine watchmaking where you're sort of working on your own. They're typically the same types of watchmakers that go into customer service as well. Because customer service, you can imagine repairing watches, you get in very different watches from very different eras, and you have to finish the job from the start to the end. And you really have to be capable to work on very different mechanisms. And sometimes that suits people more, and others enjoy really that more kind of repetitive type of watchmaking where you have the same movement over and over again.
When you're looking at some of these high complications, can you give any sense of like time and scale of how long someone might be working at one of these benches?
Yeah, so typically when you think about a perpetual calendar, we spend roughly 60 minutes on the base movement assembly steps, and then it's about 3 to 4 hours assembling the module. And then when it comes to putting it all together and testing and disassembly and reassembly, this can be many, many hours depending on the regulating process. So you can easily talk about, almost a day passing for somebody to assemble a highly complicated watch.
And that's after a decade of training to get to that point. A lot of people think about just the time, but then what was the time invested to get to that?
In Perpetual's 45 years of product development as well. So here you really have a good overview of what we assemble here in this facility. So it really is quite a range of different movements. You think about, this is our mainstay IWC manufactured chronograph movement, the caliber 69. This goes into Portugieser chronographs, pilots chronographs, and so on. Then you have a flyback chronograph, caliber 89, with a column wheel. This one is really a very robust chronograph that goes into our military aviation watches, for example. It goes into your yacht club series, for example, but also carries a ton of complications, including perpetual calendars. And then you have our caliber 59. This is probably the closest to a pocket watch movement. It's an 8 days power reserve hand-wound movement, with that huge barrel.
Almost 38 millimeters in diameter. That's insane, yes. It's bigger than most watches.
It is indeed. On the other side of the spectrum, smaller premium automatics like caliber 82. So this is really something we're using, for example, in the Big Pilot 43 or the Portugieser Automatic 40. And then our probably most signature caliber here is that twin barrel 7 days power reserve caliber 52. Coming from the Portugieser from the year 2000, then developed incrementally, carrying that first code-cast perpetual calendar in 2003, and since then being continuously developed further. And it's really quite iconic for IWC because it is the base for Big Pilot, Portugieser Automatic 42, perpetual calendars, all the big complications as well.
Chris, first time in Schaffhausen, IWC didn't disappoint. I just want to thank you so much for having us here. It was a real treat to see behind the scenes and just how your watches are ultimately created.
Thank you so much for coming, Teddy. This was fun. And to all your viewers as well, everyone's always welcome to Schaffhausen. I'd love to show you guys around.
Great meeting you, Chris. Thank you.
Thank you so much. Thank you.